Now we want to take on the acceleration function, and we'll just look in one dimension. What you need to know is right here. The acceleration function is the time derivative of the velocity function. You need to memorize this expression. Don't worry about any equations or anything else, because this statement is always true, and then you can apply it to whatever mathematical representation in which you're interested. So if we're in one dimension, and let's call that, label that one dimension the x-axis, we have some position function x of t that tells us the location of an object as a function of time in this one dimension on the x-axis. And we found out before that the position function, the velocity function of time, which is also going to be along the x-axis because it's constrained to move in one dimension, is in the time derivative of the position function. And so now the acceleration function, which is also confined to be along the x-axis, will be the time derivative of the velocity function, or the second time derivative of the position function. And so if we know the position function, then we can calculate both just by calculating the derivatives. Let's do a couple easy examples. So if I have a position function that's equal to 20 minus 10t, I can differentiate that to find the velocity function of time, and the constant is 0, which is then minus 10, and this is in meters per second. If this is in meters and time is in seconds, then the velocity is in meters per second. I can differentiate this again to get the acceleration as a function of time, which is then 0, because this is a constant and the derivative of a constant is 0. Okay, so let's look at something only slightly more interesting. So now we'll do 2t minus t squared. Okay, so if I differentiate this once, I get the velocity function in time, which is 2 minus 2t. And now I can differentiate this and get the acceleration as a function of time. And I differentiate the 2's, get 0, differentiate minus 2t, and I get minus 2. And now meters per second squared is the units of acceleration. Let's take a minute and look at what that means. So meters per second squared is the units of acceleration. Another way to look at that is that's meters per second over seconds. And so the acceleration is telling you how the velocity is changing. And so it's saying that the velocity in meters per second is changing some amount for each second. And so, for example, here if I have negative 2 meters per second squared, I can write that as negative 2 meters per second. So that's saying if this acceleration lasts 1 second, then the velocity will change by a negative 2 meters per second. That's sort of what the meters per second squared means, and it's linked to how the velocity is changing. Okay, so to connect to things that we've talked about before, we can talk about differences of acceleration at 2 points in time. Let's say I choose an initial time t sub I and some final time t sub f. I can calculate some time difference, which is t final minus t initial. So if I look at 2 points in time, then I would have an initial acceleration. Now I might call this initial acceleration a sub I, but that's really the acceleration function evaluated at the initial time. And then I would have a final acceleration. I might call that a sub f, subscript f, but that's really the acceleration function evaluated at the final time. And if I want to know, I can calculate the acceleration difference. The acceleration difference is I might call that delta A, which is then the acceleration final minus the acceleration initial, which I find by calculating the acceleration function at the final and initial times. And then if